Today we're going to start chapter 9 and we're going to look at section 9.1, Introduction to Sequences. Now, we went pretty quickly through trigonometry. Now we're going to go pretty quickly through sequences. So this is just kind of an introduction to it, and you'll get much more detail when you get to trig pre-calculus next year. But we'll get started. So in this lesson, you'll be able to write the terms of sequence, and we're going to describe what a sequence is, and write the rules for sequences. Okay, so here's some of the terms we have to know. Sequence is a function whose input, or the domain, consists of consecutive integers. If it does not tell you what number to start with, assume that it starts with 1. Now, sometimes we start with 0, but in general, we'll start with 1. So the terms, we could have an example of terms of an output, which is the range of the sequence. We could have something like this, 3, 5, 7, 9. That would be considered what we call an arithmetic sequence because it differs by 2 every time. Now let's take a look at the domain of this. Again, the first, second, third, fourth, all the way up to the nth element. And the range, in this case, would be 3, 5, 7, 9. So a way to write that would be using this explicit rule, a sub n, that's what I will call it, a sub n, as a function of n. So a sub 1 is equal to 3. So that means the first term is equal to 3. A sub 2, that means the second term is equal to 5. A sub 3, that's a 3 there, is equal to 7, and A sub 4 is equal to 9. Now we could write a general expression this way. A sub n is equal to 1 plus 2n. Now we could have figured that out because if n is 1, n times 2 would be 2 plus 1 would be 3. If n was equal to 2, 2 times 2 would be 4, plus 1 is equal to 5. So a sub n is, we could write it this way. Okay. Now, recursive rule gives the beginning terms. Each successive term is related to one or more of the preceding terms. So let's take a look at this. A sub 1 is equal to 3. We could write that as a sub n is equal to a sub n minus 1. That means the previous term plus 2. So anytime we know what one term is, we know what the next term is because we can add 2 to it. So a couple of other terms, finite sequence. It has a beginning and an end. It starts with 3, 5, 7, 9, and we go up to 15, let's say. And that's where we terminate. An infinite sequence has a beginning, but it has no end. And we would write that as 3, 5, 7, 9, dot, 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 means it goes on for eternity, okay, all the way into infinity. All right, so let's take a look at some examples here. Before we get to that, let's talk about the Fibonacci sequence. In 1202, Italian mathematician Leonardo Fibonacci described how fast rabbits breed under ideal circumstances. He created an imaginary set of ideal conditions under which rabbits could breed and posed the question, how many pairs of rabbits will there be a year from now? Fibonacci noted the number of pairs of rabbits each month and formed a famous pattern called the Fibonacci sequence. So an easier way to look at this is we start with 0 rabbits, we add 1 to it, and we have 1 rabbit. Take that 1 rabbit, add another rabbit, we have 2 rabbits. 2 plus 1 is equal to 3, and 1 plus 2 is equal to 3. And then 2 plus 3 is equal to 5, and so on and so on. And this number could keep growing and growing. So we could have something like this. 1 plus 1 is 1. 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. And then 21, 34, 55, and so on and so forth. That is what is called a Fibonacci sequence, and it's very common in mathematics, and it's also common in nature as well, in certain growth patterns. So we'll look at more at that later. But that's a term that you're going to want to remember, the Fibonacci sequence. All right, let's get back to this sequence here. Let's write the first 5 terms of a sub n is equal to 2n plus 5. Well, if n is 1, a sub 1 is equal to 2 times 1 plus 5 would be 7. A sub 2, 2 times 2 plus 5 would be equal to 9. A sub 3 would be 2 times 3 plus 5 is 11. A sub 4 would be 2 times 4 plus 5 is 13. A sub 5 would be 2 times 5 plus 5 is 15. So our first 5 terms would be 7, 9, 11, 13, 15. Okay, now let's take a look at the next one. We're given the first term, and then we're given an equation for each subsequent term. So let's take a look at how we could calculate this. So I know what a sub 1 is, it's negative 5. A sub 2 would be the previous term, which would be a sub 1, which is negative 5, minus 8 is negative 13. Then negative 13 minus 8 is negative 21. The negative 21 minus 8 is negative 29. And negative 29 minus 8 is negative 37. And so the first 5 terms of this sequence would be negative 5, negative 13, negative 21, negative 29, negative 37. So writing rules and graphing sequences. Now we can do this with our calculator, but we're not going to do that right just yet. But you might want to check out some YouTube videos or some other videos of how to do this on a calculator. But if the terms of a sequence have a recognizable pattern, then you can write the rule for the nth term. So some things to look for a constant difference. Okay, that's what we call an arithmetic sequence. Look for a constant ratio. That's what we would call a geometric sequence. For instance, if I did something like 2, 4, 8, 16, I'm increasing by a factor of 2 every time. That's called a geometric sequence. Look for oscillating signs, back and forth, positive, negative. That would mean we are multiplying by a negative number. Try factoring the terms to look for a pattern. Remember, the term number has to be related to the term itself, and we'll take a look at an example of that. And to graph, then let the x-axis be the domain. So 1, 2, 3, 4, 5, each n for each term. And then the y-axis be the range. What is the a sub n value? All right, so let's write the rules for sequences. Okay, in finding the pattern. So describe the pattern, write the next term, and then write the rule for the nth term. So any term in that sequence. So I could have 2, 5, 10, 17, 26. Okay, what is our rule here? Well, if I look, I'm not increasing by a constant difference. Okay, the first difference is 3, and then 5, then 7. And look, I got 9 here. But my second difference is 2. So that tells me it's going to be some sort of n squared term. And I could figure out that if n sub 1 is equal to 2, so that would be n squared would be 1 squared plus 1. So 1 squared plus 1 would be equal to 2. 2 squared plus 1 would be equal to 5. 3 squared plus 1 would be equal to 10, and so on and so forth. So that's a rule for that pattern. Let's take a look at this one. Here, it looks like we have a common difference, and it's negative 4. So it's just going to be n to the first power term. So it's going to be just simply negative 4n. So uh, n sub 1 is negative 4. N sub 2 would be negative 8, and so on and so forth. So not too hard there. All right, let's look at a real world application. A ball is dropped and bounces to a height of 4 feet. The ball rebounds to 70% of its previous height after each bounce. Graph the sequence and describe its pattern. How high does the ball bounce on its 10th bounce? So if it bounces 4 feet on the first one, and then it's going to bounce 70% of that, and then 70% of that, then 70% of that, and 70% of that, all the way down until it's just negligible here, right? So a sub 1 is equal to 4. A sub 2 would be equal to 4 times 0.7. A sub 3 would be a sub 1 times 0.7 times 0.7 again. So we are going to multiply by 0.7 n minus 1 times from our a sub 1. So every bounce after we let go is going to be 0.7 of the previous. So that's why we're going to keep multiplying by 0.7. So now that we have this formula, we can simply plug in a sub 10 is equal to 4 times 0.7 to the 9th power. And if we do that, it's approximately 1.61 feet. I'm sorry, 0.161 feet. All right. Many patterns repeat over and over. Each step in this repeated iteration process is an iteration, repetitive application of the same rule. I already got the answers here for you. Find the number of triangles in the 7th and 8th iterations of the Sierpinski triangle. See above. So here we have 1, and then 3, and then 9. So what does it look like? It looks like we have a sub 1 is equal to 1, and then each one after that is going to be 3 times that. So a sub n is going to be 3 times a sub 1, okay? And then a sub n is just going to be 3 times n to the first power. So what about the 7th and 8th iterations then? A sub 7 is 3 to the 7 minus 1, or 3 to the 6th power, is 729. And then a to the a sub 8 is equal to 3 to the 8 minus 1 power, it's 3 to the 7th, is 2187. And you can see that this grows quite quickly, quite rapidly. All right, so our homework for today is listed there, and there's some Alex suggestions. I also suggest that you take a look at the examples in the textbook to help you with your homework. We kind of went quickly through this lesson, but I wanted to give you time to work on the homework. So if you get stuck, go and look at the examples in the book. I think that'll help you. So that's all we're going to do for today.